Kubernetes and GKE Part 22. This episode has 4 questions. For each question, take a moment to think through your own answer before I share a strong approach. Question 1. Explain persistent volume claims. Here's a strong way to approach it. A persistent volume claim, PVC in Kubernetes, is a request made by a pod, or user, for storage resources like size and access mode, without needing to know how the storage is actually provided. Core idea: a PVC is like a storage request ticket that asks for a persistent volume. It abstracts storage consumption from storage provisioning. Why PVC is needed in Kubernetes. Pods should not deal with storage details. Storage can come from different backends: cloud, NFS, local. So, admin creates storage. Persistent volume. User requests storage. PVC. Kubernetes binds them automatically. How it works. Flow. 1. User creates a PVC. 2. Kubernetes searches for matching persistent volume. PV3. If match found, binding happens. 4. Pod uses PVC to mount storage. 5. Data persists beyond pod life cycle. PVC versus PV feature. PVC PV role requests storage. Actual storage created by developer or user. Admin or dynamic provisioning. Scope namespace cluster binding consumes. PV gets bound to PVC. Example: PVC YAML API version v1 kind. Persistent volume claim. Metadata: name, my PVC spec, access modes. The exact commands and code are in the written question bank. Nice. Let's continue. Question 2. What is storage class? Here's a strong way to approach it. A storage class in Kubernetes defines how storage should be dynamically provisioned and what type of storage should be created for persistent volume claims. PVC's core idea: storage class is a blueprint that tells Kubernetes how to create storage automatically when a PVC requests it. It removes the need for manual persistent volume creation. Why storage class is needed? Without storage class, admin must manually create persistent volumes. PV not scalable in cloud environments. With storage class, PVC automatically creates PV. Storage is provisioned on demand, fully dynamic and cloud native. How it works. Flow. 1. User creates a PVC. 2. PVC references a storage class. 3. Storage class tells Kubernetes what type of storage to create, which provisioner to use. 4. Kubernetes dynamically creates PV. 5. PV gets bound to PVC. 6. Pod mounts the storage. Example: storage class YAML API version, storage K8SIO or v1 kind. Storage class metadata: name, fast storage provisioner, Kubernetes IO or OSEBS parameters. Type: GP3. Reclaim policy: delete volume. Binding mode: wait for first consumer. Key fields: 1. Provisioner defines who creates the storage: AWS, EBS, Azure Disk, GCE. Persistent disk, CSI drivers. Modern approach. 2. Parameters defines storage type or config: SSD or HDD. Performance class: GP2, GP3. IOPS settings: 3. Reclaim policy: delete storage removed when PVC is deleted. Retain keeps data after PVC deletion. 4. Volume binding mode: immediate PV created instantly. Wait for first consumer: waits until pod is scheduled. Better for zone awareness. Storage class versus PVC component role: storage class blueprint for storage creation. Persistent volume: actual storage resource. Persistent volume claim request for storage. Types of provisioning: 1. Static provisioning: PV created manually. PVC binds to existing PV. 2. Dynamic provisioning: storage class, PV created automatically, no manual intervention. Simple analogy: think of a storage class like a menu in a restaurant. Storage class equals menu item, e.g., SSD storage. PVC equals order placed by customer. PV equals actual meal prepared in kitchen. Real-world use cases: cloud block storage, AWS EBS, Azure Disk, high-performance SSD storage, database storage, MySQL, PostgreSQL. Stateful applications. Key benefits: automation of storage provisioning, cloud-native flexibility, no manual PV management environment. Specific storage types: interview-ready definition. A storage class in Kubernetes is an API object that defines the provisioner, configuration, and policies used to dynamically create persistent volumes for persistent volume claims, enabling automated and scalable storage provisioning in a cluster. Great. Moving on. Question 3. Explain init containers. Here's a strong way to approach it. Init containers in Kubernetes are special containers that run before the main application containers in a pod and must complete successfully before the app starts. Core idea: init containers are like setup tasks that prepare the environment before the main application runs. They run sequentially, one after another, and only once per pod start. Why init containers are used: they help handle pre-start dependencies, such as waiting for a database to be ready, downloading configuration or code, setting up files or permissions, running initialization scripts, checking external services how they work. 1. Pod starts. 2. Init containers run in order. 3. Each init container must complete successfully. 4. If any init container fails, pod restarts, based on restart policy. 5. After all init containers succeed, main containers start. Key behavior: run before app containers run sequentially, not parallel. Must finish successfully, not restarted unless pod restarts. Example: YAML version v1 kind. Pod metadata: name, my app spec. Init containers: name, initdb. Check the exact commands and code are in the written question bank. Alright, next question. Question 4. What are sidecar containers? Here's a strong way to approach it. A sidecar container in Kubernetes is a helper container that runs alongside the main application container inside the same pod to provide supporting functionality. Core idea: a sidecar container enhances or extends the main application without changing its code. It runs continuously alongside the main container, not before it, like an init container. Why sidecar containers are used: they help offload common responsibilities such as logging, monitoring, proxying, traffic security, handling configuration, syncing, service mesh functions. How it works: main container runs the application, sidecar container runs helper logic. Both share network namespace, same IP storage volumes. If defined, they communicate via localhost or shared files. Common use cases: 1. Logging agent collects logs from app and ships to Elk or CloudWatch. 2. Monitoring agent exposes metrics. Prometheus exporter. 3. Service mesh proxy. Example: Envoy proxy in IceGeo handles traffic routing, retries, TLS. 4. Config sync watches config changes and updates app files. Example: YAML version v1 kind. Pod metadata: name, app with sidecar spec. Containers: name, app. The exact commands and code are in the written question bank. Let's keep going. That wraps up this episode. Nice work practicing, and see you in the next one.